probability. In this lesson, we'll study the odds of stuff happening. So, first, 0% chance of happening or impossible stuff doesn't happen, you say 0. That's the lowest you could go, right? It doesn't make any sense to say, oh, there's a negative 5% chance of stuff happening. The lowest is 0. 0 is the lowest. Likewise, the highest probability of something happening is 1 or 100%. Right? That's why when you hear people go, oh, there's 110% chance of rain tomorrow. That's dumb. The highest you can do is 100. 100 is the max. As you can see here, likely happens anything above 5. 5 is an equal chance. It's like a flipping a coin, right? It's a 50-50 shot. Anything below that's less likely to happen. The main thing to take away from this is that 0 is the lowest probability of something happening, and 1 is the highest. Right? So either 0% or 100%. That's where all our ranges should go from. So keep that in mind. 0 to 1. Everything should I can't not highlight. Everything you want is between 0 and 1, since I screwed up that 0, 1 right there. Right? Nothing higher, nothing lower. We're going to talk about two types of probabilities. Experimental probability, which is all based on like actually doing an experiment, like actually flipping a coin or actually rolling die and counting them up. And then there's also theoretical probability, which is based on some mathematics. So you figure out the math of the odds. It's like, oh, there's 1 out of 6 chance of doing this. So first we're going to talk about experimental. Now the key thing for all probability and a lot of stats in general is one thing. If you want the probability of something, I always say it's want over total number. That's the key to life, people. It's not 42, it's want over total. You do that, you'll be fine for the rest of the stats. Now let's look at an example. So here in this example, some unruly office executive dropped 145 paper clips onto a piece of paper. He wanted to see how many fell onto the line, how many fell inside the line. Right, so in this case, he observed that 113 fell completely inside the square. So right here, 113 fell completely inside the square, and 32 fell on a line. So he wants to find two decimal places the experimental probability of clip falling inside a square. Right, so you know what the key to this is? It's like the key of all stats: want over total. Right, my total paper clips is right here, 145, so that's my bottom. The ones I want, well, inside a square, so that's my 113. And there you go. That's how easy it is. Right, how many fall in line? Well, I'm just going to use want over total again. So my want is 145, my total is 145, sorry. And I want the ones that fall on the line, which is 32. And there you go. That's the answer. If I had a calculator, I'll plug it in, get some decimals, but honestly, either way is fine. They both work out. So that's that one. Now let's move on to another quick example. Pat does a lot of traveling in her car. She keeps records on how often she fills her car with petrol. So basically, over here is the day between refills, right? So 1 day between refills, 37. That's some low mileage. 2 days between refill, 81 times. 3 days between, 48. She must be driving like a muscle car or something. 4 days between, 5 days between, that's 6 days. She must have not gone anywhere. So the question is, so this is how many times she filled up within those days of refills. So the question is there a 4-day gap? Estimate the likelihood that there's a 4-day gap between refills, right? So remember our key, want over total. So I want 4-day gap. That's this one. So there's 17 4-day gaps. And there's a total. Well, look, I gotta do like a little cumulative frequency. I'm lazy, so I'm just gonna do this. Hey, look at that. Me run the shortcuts. Right? And you get that. And I get 17 over 190. Add all that up. So that's the first one. Now B's a little different. There's at least a 4-day gap, right? So it means 4 or more. At least 4. People always get this wrong. It means 4 is the least, right? I want at least 4 cookies. 4 or more. Give me 4 more cookies, please. Right, so more. Right, so it has to add up all these. So 4 plus 6, 23, 24. So 1 over total. This is going to be 24 over 190. So the odds that she needs at least a 4-day gap is 24 from 190, whatever that small percentage is. Get a new car, girl. So the examples we've done have been pretty easy. So sometimes they're not so nice. So when that happens, we might want to use a sample space. What that means is just a way to write out your outcomes, like all the different possibilities. So a ton of ways to do this. This list is probably the basic one, right? Table of outcomes we'll talk about later. Two-dimensional grid I'll show you in a second. Venn diagrams, that's gonna be probably the next video. And same thing with tree diagrams. We'll talk about them. We'll have a whole section on just those two because they're super important. But to show you an example of how you do a list, let's look at what a sample space is. Let's talk about when you toss a coin. Right, when you toss a coin, there's two choices. You could get heads or you could get tails. And that's your sample space. A little set notation. You get a head or you get a tails. Done. Right? When you roll a normal die, right? When you roll one die, it's gonna be 1, 2, 3, 4, 5, or 6. Right? It's the only numbers you could get when you roll a die. That's a sample space. So now you know. You'd be like, okay, what's the odds of getting a 3? Well, there's only one 3 out of a total of 6. Right? So it gives you all the options laid out nicely. Now let's look at two-dimensional grids. So right, sometimes when you're looking at two options, you want to do a two-dimensional grid. This helps you space out your information better. So here's a quick example. Someone's tossing two coins, so you're gonna get heads, tails, heads, tails. So if you want to space that out a little better, you can just go draw a little X and Y axis. Let one of them be coin 1 and the other one be coin 2. There's my straight lines again. Right? And then you can see all your possibilities. There's heads, 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 tails, tails, heads, tails, tails, tails. Right? So it's just a nice, easy way to show you your possibilities. That's all a two-dimensional grid is, a way of writing out your information. We'll do an example of that a little later. Another thing we could do is tree diagram. And again, we're actually going to talk about this in great detail later, but this will give you a little preview, a little trailer. Using tree diagram. So a tree diagram, if you're tossing two coins, you should start right here. You make a little tree. You could get heads or tails. All right, this is coin 1. This is us. Right, I could either get heads or I could get tails. And then once you do that, you can roll again. So you could get heads or tails. That's like a tree diagram. That's what it looks like. Coin 1, coin 2. Real quickly, drawing two marbles from a bag containing red, green, yellow marbles. So when you draw one marble, you could get red or green or yellow. Again, I like to draw us. And then once you do that, you can do it again. So red, green, yellow. Red, green, yellow. Hopefully your things are nicer than mine. Red, green, I'm not sure that's why it's in yellow. So that's what the tree diagrams look like. Again, we'll do this more. We'll have a whole section on this later. So now that we've done experimental probability, where you just look at the data they gave us, now we're going to do some theoretical probability. So you have to do a little more work. You actually got to think about the odds of stuff. But the normal rule still applies. Probability of anything is just want, right? How many of those things do you want over the total number? Or in more formal terms, this right here. Don't forget what I said before, right? Where when we talk about probabilities, the max is 1. Right? It never makes sense to have over 100% probability of something happening. The max that's going to happen is 100%. That means it's guaranteed to happen. And likewise, the least that could happen is 0. If there's a 0% chance of something happening, then there's no chance of it happening. It's not going to happen. It can't get any lower than that. So that's the min. This means no chance. This is guaranteed. So let's look at a quick example just to illustrate that point. A ticket is randomly selected from a basket containing 3 green, 4 yellow, and 5 blue tickets. So this real quick math right there. 3 plus 4 plus 5. So I get 12 total tickets. Right? I'm going to need that for the 1 over total. So over here, what's the odds of getting a green ticket? Well, there's 3 green tickets. Right? 1 over total. 3 over 12, or 1/4. Or 25%. So there you go. B, a green or yellow ticket. Oh, they're trying to be a little tricky. Green or yellow. So there's 3 greens. There's 4 yellows. So a total of 7 tickets you want over the possible 12. So 7 over 12. C, an orange ticket. If you look, there's no orange ticket at all. So there's no chance you're going to get that. So you just put 0, right? How many do you want? There's none there. So 0 over 12. Or 0%, right? Lowest you could get 0. Right, and this one says green, yellow, or blue ticket. So for that one, I want green, yellow, or blue. That's all the tickets. Right, so I'm going to get 12 over 12. Right, I'm guaranteed to get one of those colors. One color's in there. So 100%. So 1 or 100%. Right, you're guaranteed to get one of those tickets. That's how it works. Let's look at another quick example. This isn't covered, so I'm not going to go over it in total. But an orange 6-sided dice is rolled once, determine the chance of, right? So keep in mind, when you roll a dice, right, if we have a list of outcomes here, when you roll a die, let's see if I could draw one. Alright, and little die right there. Right, you could get a 1, a 2, a 3, a 4, a 5, or a 6. Right, oh, also right here. So what's the odds of getting a 6? Well, there's only one of those, so 1 out of 6. Of not getting a 6, right? So you want anything but a 6. And we'll have a whole special way of doing that later. Well, there's 1 6 and there's not. Everything else is not a 6, so 5 out of 6. 1 or a 2? Well, there's 2 of those. It's either 1 or a 2. So 2 out of 6 or 1/3. Not a 1 or a 2. So everything's not that. The rest. So there's 4 of those. So 4 out of 6 or 2/3. That's the general idea. So this next example we're going to look at, this I'm going to use to demonstrate the power of how useful sample spaces could be. So this is 6 different orders in which Anita, Kai, and Nita may sit in a row. And then once we do that, we're going to, what's the probability that we run and select something that has Anita sit in the middle? If I do this normally, just like off the top of my head, it's going to be hard for me to figure out how many times Anita sits in the middle. So the best thing to do is just do sample space real quick, right? You got Anita, Kai, and Nita. And then let's just keep Anita in the front and try to switch these two. And like, okay, those are all the ones with A's, so now let's put K in the front. So K-A-N, and then you can switch these two, so K-N-A. And then we'll go with N in the front, so N-A-K. And then switch these two, and K-A. Right, so now there's 6 total. How many doesn't have Anita stay in the middle? Well, 1, 2, so 2 out of 6. Anita sits at the left end, so 2 out of 6. Anita does not sit at the right end, so she's not at the right end, so not this one, not this one, so there's 4. K and Anita are sitting together, so I'm looking for KN together, so KN, 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 so NK, so we have 4 of them, 4 out of 6. Right, to me that was made a lot easier by using sample spaces. So now let's talk about complementary events. We kind of actually briefly talked about this, brought it up earlier. This is 2 events that are the opposites of each other. So like, if I'm looking at rolling a die, right? We talked about this before. If I was gonna roll a die, which is 1, 2, 3, 4, 5, 6 choices. The odds of rolling a 2, well, there's only one of them, so 1 out of 6. The odds of rolling not a 2, so what we'd say not, or is we put a little dash right here. So not a 2 means anything but a 2. Well, it's everything else. 5 out of 6. If you notice, if you add those 2 probabilities up, you get the whole thing. You get 6 out of 6, or 1. That's why I have complementary events. They're each other's opposites, each other's inverse. So this is the formula in your formula sheet, right there. If you ever get something that's not that, if you add them up, you get 1. So the way we actually use this a lot is this. Probability of A prime, A naught, is this 1 minus probability of A. That's probably the way we actually use it the most, but it's the way you can see in the formula sheet. Let's just do one quick example. If the probability of A naught, that's supposed to be a naught, the font's a little weird. Find the probability of A naught if probability of A is 0.7. Well, right? Well, probability of not A is just 1 minus probability of A. So 1 minus 0.7, 0.3. Right? If there's a 70% chance of A happening, the opposite of that, or the inverse of the complement of that, is going to be 30%. Now let's look at an example that kind of illustrates this point a little bit. So a carton of dozen eggs contain 8 brown eggs and the rest are white. How many white eggs are there in the carton? Well, we could just count. 1, 2, 3, 4. 4. Boom, killed that. Final probability that egg selected at random is brown. So the way you could do that, right? There's so we know there's 4 white eggs. So this could just simply be, so there's ways you can do it, right? You could count it 1, 2, 3, 4, 5, 6, 7, 8. Go 8 out of 12 dozen eggs. Or you could go, well, there's only 2 types of eggs, so this is the same thing as not white, right? And then we go 1 minus how many are white? Well, we counted 4, so 4 out of 12. So a little common denominator. And you go 8 out of 12. Right? So that way works too. How many white eggs are there? 4 out of 12. Done. Now let's go look back at how to use two-dimensional grids to solve some problems. We're going to look at a couple of these. So remember, two-dimensional grids is a way of writing stuff out, information out, so laying it out so you could see it better. So like our first quick example, right here we're tossing a coin. Sorry, heads and tails. It's an H. It's an H. And rolling a die, right? So 1, 2, 3, 4, 5, 6. Right? If you're trying to figure out like what's the odds of getting a head and a 6, it might be a little weird. But if you do a little two-dimensional grid, which they have laid out for us nicely right here, right? You put heads, tails. You put 1, 2, 3, 4, 5, 6 on this side. It doesn't matter. You can switch it up too. Now it's actually a lot easier to find things. What's the odds of tossing a head? Well, here's heads. So 1, 2, 3, 4, 5, 6. So 6 out of 12, or 1/2, as they demonstrate down here. That's me underlining it and highlighting it, not crossing it out. What's the odds of getting a tail and a 5? Right now, this is where it really comes handy. Getting a tail, so these 6, or getting a 5. Okay, I did that wrong. Getting a tail and a 5, so tail and a 5. Very important, and. Right, so a tail and a 5 is tails and a 5 right there. Sorry about that. So 1 out of 12. It only happens once. Getting a tail or a 5 is what I meant earlier. Right, so in that case, you could get a tail, one of these 6, or you could get a 5. So you have the extra one down there. So you have the 6 out of 12 plus the 1 out of 12. 7 out of 12. So that's how you can do two-dimensional grid to help you. And we're actually looking at another quick example to even hit it home even more. And look at this one. We're not going to do all of them, so relax. But if you're going to throw, what's happening here, we're throwing 2 die, right? We're doing like we're playing craps. So we're going to throw 2 die. Each have 6 possibilities. And if you're just doing that normally, it might be kind of hard to figure out all the possibilities. Now, some of them are easy. What's the odds of getting 2 3s? Well, that only happens, a 3 and a 3 happens 1 time. So 1 out of 36. Right, there's 36 probabilities, so there's 6 here and 6 there. But let's look at something else. Like, what's the probability of getting no 6s? So you don't want any 6s. So if you have this two-dimensional grid here, you just could look at the no 6s. It's this 5x5 grid that I expertly highlighted. So 5x5, just 25 of those. I have no 6s at all. So 25 out of 36. Or what if you wanted at least 1 6, right? At least 1 6. So it'll be 6 1. It'll be all these plus all these. All these have at least 1 6. So 6 plus another 5, 11. It's an 11 out of n. It was an 11. Don't judge. Or you could also a lot of this is easier with the grid. So let me erase this real quick so we could look at one more example of this type. We have the finest erasing technology, as you can see. No expense spared. Okay, let's look at one more. Is sum greater than 8? So this is much easier with the grid. So I'm like 6 and 1. No, that's only 7. 6 and 2, 8. But I want greater than 8. So 6 and 3 works, right? 6, 4. All these are gonna work. How about 5? 5-2, 5-3. Again, still 8 well greater than it, so it's going to be 5-4. It's going to be all these. That's my perfect, again, perfect circling. 4-2, 4-4, 4-4-8, but a little higher, right? 74. I don't know why I made an 8 there. And then here, 3-1, 3-2, 3-5 is still 8, but 3-6 it's me a little bit more, 9. Now, if you count these up, if you ignore my highlighting, you get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's 10 numbers that are greater than 8. Right? This is a way that's so much easier than actually writing out other possibilities. It's easier than going 1-1 and 1-2 and 1-3 and 1-4. If you do a little grid here, it really just spreads out your information and makes it really easy to solve things. Now let's go big time and make our own grid. That's right. We got there. Draw a grid of the sample space with the 5 cent and 10 cent coins are tossed simultaneously, hence decide the probability of getting each of these. Right, to make a little thing here. It doesn't matter which one. Let's make this the dime. And this the nickel. That's the nickel. Right? So basically you get heads or tails. So straight line, heads, tails, heads, tails. And you see all the times they cross. Right, there's 4 possibilities. You get heads, heads, tail heads, head tails, and tails tails. And the first question is, what's odds of getting 2 heads? Well, heads and heads, it's this one right there. So there's 1 out of the 4 possibilities. 2 tails, same thing, down there, 1 out of 4. Exactly 1 head. So this has 2 of them, you only want 1. So this one counts, right, because it's head tails. And this one counts, right, because it's head tails the other way. So 2 out of 4. Then at least 1 head. Don't laugh. So head tails, tails heads, heads heads. So 3 out of 4. Right? At least 1. So as long as you get 1, you're good. Now let's move on to another topic of probability. Table of outcomes. So this is one of the most straightforward type of problems you will see in probability. They'll ask a question, they'll give you a table of what happened. So people exiting a new ride at the theme park were asked whether they liked it or disliked the ride. The results are alongside. So right, this is an experimental probability. Right, so they give you either people liked the ride, didn't like the ride, challenged adults. Now there's one rule, one thing you gotta keep in mind for table of outcomes. There's one trick to table of outcomes that makes your life so much easier, and that is add, if they don't have it already, add a totals column and row. Totals, row, and column. It's so essential. So you see how you have child, adult. That's great, but what you're really gonna need is total. So I add a little total right here. Add these up, 55 plus 30 ish. So I get 80. Let's see, 83. So then here, 17 plus 30, so I get 47. And then you still do the same thing down here. Totals. 55 plus 17, so 2 there, carry the 1. And 28 and 30, so I get 58. Run these up, so I get 60, I get 130. Right? And that's super important for a lot of different reasons, right? Because if they ask me how many people like the ride right here, I'm gonna have out of these two things anyway, 55 and 28. And they ask me what the probability is. Remember, I meant to highlight that. Probability is. Remember our normal rule? Want over total. So for this very first one here, like the ride. How many people like the ride? I need the number of people that like the ride. So the total number of them, 83. And now I can put over the total of the whole thing, 130. Right? How many people actually went on the ride? And then you can get a little more specific, like right here. Is a child and disliked the ride? What's odds that it's a child and they didn't like the ride? Well, you have it. Child disliked it, 17 out of the whole total, 130. Now it gets a little tougher. Is an adult or dislike the ride? So is an adult is this right here, right? Adult 58. You added this one and this one. Or dislike the ride. So You added both adults, so that's already taken care of. But you still got to add this missing child that disliked the ride. So your total is going to be whatever 28 plus 30 plus 17 all over 130. Right? Is an adult. So got your 2 adults. Or dislike the ride. So you already had this one counted. You said I count the extra one. You haven't gotten it yet. Like the ride, given that he or she is a child. So now here it gets even more complicated, but still fairly easy. Here's the key thing. Given that. So they're telling you, you know this person is a child. So the key here is that's your new total. It's your new world, basically. The only thing you're looking at is that right there. So you know this person is a child. So right here, right? Only look at the child, because that's all. Because we know all we know is that they're a child, right? So given that here she's a child, so we're looking only at the children now. How many of them like the ride? So my want is like the ride, but now we're only looking at children, so 55. And the total is the children, number of children there are, 72. And that's the answer for that one. So let's practice that same idea right here. Right? Is an adult, given that he or she disliked the ride. So again, your total is just dislike the ride. That's your total. So when people are looking at it, it's dislike the ride. So look at this little box right here. If you can see through all that Jason Pollock of writing there. So my new total is just going to be dislike the ride. So 47. And then the question is, how many of them are adults that dislike the ride, right? So is an adult. So of the people that dislike the ride, 30 of them are adults. And that's the idea. So now we can move on to another example. We can do all by ourselves. A small hotel in London has kept records of all the room bookings made for the year, categorized by season and booking type. Find probably that the randomly selected booking was blah blah blah, right? In peak season. So again, when I see something like this, the very first thing you want to do with this table of outcomes is make a totals column or row. Right? It's essential to this stuff. You want to go over here, put total. Here, put total. Add up those values. I'll do that right now. Okay, so there's all the totals. Save you guys some time. So first one, find probably that they booked the room in peak season. So again, right, the key to all this is just 1 over total. Key to this whole lesson, right? I want how many rooms are there in peak season total? How many total rooms are there in peak season? 443. And how many rooms were rented in total? 1035. Right, B, single room in off-peak season. So you want a single room and you want it not to be in peak season. So 248. So just go 248 over the total. Right? Single or double room. So there was 373 single rooms. And you add that to the number of double rooms and divide that by 1035. Right? Now let's get to the real ones, right? The given that one. So ones that are a little bit tougher. Find probably that someone rented a family room given that it was in the off-peak season. Right? So only thing you know is that it wasn't in peak season. So you're only looking here. It was not in peak season. So just off of that, we know the bottom is going to be 592. Because that's how many total rooms were rented in off-peak season. And I'm on a family room. 152. Next, in the peak season, probably they rented a room in the peak season, given that it was not a single room. So again, this is your new total. You know it's not a single room. So that's a little more difficult than normal. So it's not this one, right? It's a complement of that one. So it's all these. Right, it's a double or family room. So I know it's not a single room. So I got to add, for my total, I got to add 412 plus 250. They want it in peak season. So probably that's in peak season is 220 plus 98. Whatever that turned out to be would have been my answer. Moving on, let's talk about compound events. Compound events is just when two independent things happen. So when that happens, all we do is multiply them. So like, what's the odds of flipping? I think we did earlier. What's the odds of flipping a coin, getting heads, and rolling a die? You just get those two probabilities and multiply them together. There you go. So as long as those things are independent, we'll talk about what dependent means later, so you have a better sense of what independent means. All you do is multiply them. Just multiply your probabilities. That's simply it. So let's look at a quick example. Right? A coin and a die are tossed simultaneously. Determine the probability of getting heads and a 3 without using a grid. Right? So all you have to think about is like, okay, getting heads, well, you know there's only heads and tails, so odds of getting heads is 1/2. When you roll a die, we know it's 1, 2, 3, 4, 5, 6. So odds of getting a 3 is just 1 out of 6. They're independent events. You just multiply them together. 1 out of 12. And there you go. Like, that's the whole idea for this lesson. Let's do a couple quick easy examples so we can move on. At a mountain village in Papua New Guinea, it rains on average 6 days a week. So let's keep that in mind. Right? There's 7 days in a week. So it rains on average 6 out of 7 days. Determine the probability that it rains any one day. So 1 over total, 6 out of 7. 2 successive days. So remember, all we're going to do is, it was an independent event. All we're doing is multiply. 36 over 49. Done. 3 successive days. So again, that's all we do. 6 times 7 over 6 over 7 times 6 over 7. You multiply all 3 days. 216 over 343. Right? Similar thing you could say when you toss a coin, right? I'm going to toss 3 coins. Determine the probability of getting the following sequence results, right? So I'm going to toss 3 coins. Right? So when I toss 3 coins, all of them have the same probability. Getting heads and heads and heads. Well, remember, odds of getting heads is 1/2. Odds of getting heads, 1/2. Odds of getting heads, 1/2. 1 out of 8. Tails and heads and tails. Well, odds of getting tails, 1/2. Odds of getting heads, 1/2. Odds of getting tails, 1/2. 1/8. It's exactly the same. Exactly the same. I can show you with the grid, but I think you guys believe me. One final example to get really nailed at home. A school has 2 photocopiers. On any one day, machine A has an 8% chance of malfunctioning. Must not be an en masse copy machine. And machine B has a 12% chance. Still not an en masse copy machine. That should be more around 50. Determine the probability that on any one day both machines will malfunction. Right? Well, the odds of copy machine A malfunctioning is 8%. Would kill for an 8% malfunction copy machine. Machine B is 12%. Right? The independent events, you just multiply them and get your answer. Now here, look at this one. Work effectively. So that means it's not going to malfunction. That's right. It's not going to malfunction. So that means we got to use our complement thing. For machine A, that's in work efficiency, and not going to malfunction is 1 minus 8%. So 92% chance of it working fine. Machine B, same idea. 1 minus 0.12 or 88%. And if you want them both to work effectively, you just go multiply them together. Whatever that gives you is the answer. So if you look at this example right here, I just wanted to show you. A hat contains 20 tickets numbered 1 to 20. So my total is going to be 20, right? 1 to 20. If 3 tickets are drawn from the hat without replacement, determine the probability that all 3 are prime numbers. So if I'm going to do this, right, my want is primes. So I just got to count the prime numbers. And right here, later, showed the answers. They laid it all out for you. So there's 1, 2, 3, 4, 5, 6, 7, 8 prime numbers. Less than 20. Right, so the first time you draw it, well, you have 8 prime numbers. There's 20 total, so 8 out of 20. Second time you draw, well, again, you're assuming you picked 8 the first time because you want 3 prime numbers. Well, now there's only 7 prime numbers left because you picked 1. Third time, same idea. Now there's only 6. Multiply them all together, and you get that percentage chance. So that's how it works, right? Again, you just keep on multiplying. If it's without replacement, they go lower every single time because you took it out. If it's with replacement, then it's always the same thing. Okay, let's move on to one final one. A bin contains 12 identically shaped chocolates, which 8 are strawberry cream. If 3 chocolates are selected simultaneously from the bin, determine the probability of that. Now, here's the main reason I want to talk about this. Anytime they say selected simultaneously, that means you're picking them all at the same time. That is considered without replacement. So simultaneously means without replacement. Right, so I'm gonna do this like do without replacement. So they're all strawberry cream. So for A, right, there's 12 total. I want my strawberry creams. There's 8. So the first one would be 8 out of 12. I want to keep on picking. Right, I want to pick 3 chocolates. So the second one would be 7 because I picked the strawberry cream the first time. And the next one would be 6 out of 10. The last one, none of them are strawberry creams, right? So I'm going to use our complement. Right, 1 minus 8 out of 12. So 4 out of 12. Right, so the odds of getting non-strawberry cream is 4 out of 12 is the first time. Well, now you picked one of those non-ones, so 3 out of 12. 11, sorry. Now you picked another one, so now it's only 2 out of 10. And that's the idea. That's this lesson.